Hello, Chemistry 12. This is Mr. Chan, and this is lesson number 2 on redox reactions. But what we want to do is we want to focus on the standard reduction potential table again. But in this case, what I want to do is sharing the screen here, I want to focus on these numbers that we have right here on the right-hand side. So we've already talked about oxidizing agents, reducing agents, but what I want to do is I want to focus on these numbers that are here. Some of them you notice are positives, some of them are negatives, and what's going on with it. Okay, so I have the notes here. Okay, so what happens is this. When we talk about reduction, okay, the electron attracting ability of a half cell, so the electron attracting ability of a half cell reaction is called its electric potential, okay, and is measured in volts, and you've learned about that in physics. Now, those numbers that we see on the standard reduction potential table is based on the hydrogen half cell being 0 at standard state. So if we look at our standard reduction potential table, okay, what we notice is that hydrogen is 0. So all the numbers that we see there, regardless if it is positive or negative, is based on the hydrogen reduction being 0. Now, the one thing to be aware of is that it is at standard state. Standard state is the concentration of the ions is 1 molarity and 25 degrees Celsius. Okay, now what is the significance of hydrogen being 0? So all the potentials that we see are all relative to H2, so relative to hydrogen. So if we see a positive value, that means it has a greater ability to attract electrons relative to hydrogen. And negative means that it has less ability to attract electrons. Okay, so it all depends. The positive and negative basically says, is it better than or is it less than how hydrogen does? And that's something that we would have to consider. Okay, now, so let me give you an example here. So let me take this, we'll put a little star here. So let's take a look at the copper half cell. So if we look at copper plus 2 electrons to give us copper, if we look at that at the standard reduction potential table right here, okay, so let's look at copper 2 plus right here. Now notice it is a plus 0.34. So what you have is you have a voltage of plus 0.34. Now, what's the significance of this plus 0.034? So the plus means that it is better at reducing than H plus. Okay, the 0.34 is how much better? Or worse? Why did I say worse? Because if it's a negative one, then that means it's worse than H plus. So if we take a look at the standard reduction potential tables, okay, here, let's take a look at nickel. Nickel is minus 0.26. So in this case, the negative value means that negative is worse at reduction than hydrogen, okay? And by how much is 0.26. All right, now, These are all based upon hydrogen being 0. If we were to change our standards, these voltages would change. What do I mean by this? So let's say for nickel, let's say we set nickel as 0. So what would happen is hydrogen would be plus 0.26 and copper would be plus 0.60. That is if we set nickel as 0. Okay, so these values of positive or negative is dependent on which one we set as 0. But for our standard reduction potential table, we have set hydrogen as 0. Okay, now this is at standard state. So what if the concentration of the ions is not at 1 molarity? Well, depending on what the concentration of the ion is, the equilibrium will shift to restore the concentration of the ions to as close as 1 molarity as possible. So the key word is you're looking at the concentration of ions. Okay? Now, if there's a decrease in concentration, equilibrium will shift towards the reactants. And what will happen is the voltage goes down. So you can think of it, if you shift left, the voltage will decrease. This goes back to equilibrium. Okay, shift left, shift to the reactants, the voltage decreases. Now, if the equilibrium shifts to the products, the voltage increases. So you can think of it, if you shift to the right, shift to the product, voltage increases. Okay, now we're just looking at individual half reactions, but this applies also to redox reactions. So if the equilibrium is shifting to the left, then the overall redox reaction will slow down, the voltage goes down. Okay, if you are shifting the equilibrium to the right, the voltage will increase. Okay, now what I want to do is I want to go over an example in your let's say reading package. So I think it is up here on page 16, I believe. Nope, that's half reactions. Let's see, 17, balancing, I think. Let's see, nope, nope, 26, nope, nope, nope. Standard reduction potential table, yes. Okay, so what I want to do is I want to take a look at typical questions. If we have it here, this is what happens when you aren't prepared. Okay. So for each reaction and state, whether the reaction is expected to be spontaneous or not. Okay. So let's look at 36b. Okay. So 36b, what you have is you have Cu plus 1 plus Fe plus 3 gives you Cu. Oh, actually, I don't like that one. What I'm going to do is I'm going to do 3a. Okay, we have Cr plus Ag plus gives you Cr plus 3 and Ag. Okay, now they already balanced the equation for you up at the top, but I'm not going to do that right now. So again, what you want to do is you want to take a look at which one is oxidizing, which one is reducing. So for oxidizing, what you have is you have chromium to chromium plus 3 electrons. Okay, now for the reduction, we have silver plus 1 electron gives you silver. Okay, now you want to take a look at the voltages of the individual half reactions. Now, for the reduction of silver, if we look for silver here, if we go all the way down to silver, okay, so we look for silver, the reduction of silver, silver, it's right here, okay? So silver is plus 0.8. So if we go back up to my notes here, page 36, here would be plus 0.80. Now, notice for chromium, we are undergoing oxidation. So how do we resolve the idea of oxidation here? How do we find the voltage? Well, we look for the reduction of voltage of chromium. Where's chromium? It's right here. Now, notice this is minus 0.74. But this is for the reduction of chromium. Okay? What we have here, if we take a look on page 36, since we have the oxidation, we need to flip the sign, so 0.74. So here, you flip the sign. Okay? You flip that sign. Okay? Now, remember, before we can combine them, we have to balance the electrons. So for silver, I have to multiply by 3. But here, for this number, do not multiply voltage. You don't multiply the voltage. Okay? And then what you do is you add this up. You get your equation, which is Cr plus 3Ag plus gives you Cr plus 3 and 3Ag. And when you combine the two voltages together, you get 1.54 volts. Okay? Now, here's the thing. Since voltage of reaction is positive, therefore reaction is spontaneous. Okay? Now, couple of things. Remember when we talked about spontaneous reactions, when we went back to our notes, remember I said location, 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 location. When I introduced the standard reduction potential, remember I would say like upper left, lower right, etc. Okay? Now what we do is we can quantify it as well by looking at the voltage. So we can say not just upper left or lower right, but now we say that since it is a positive voltage, the reaction overall is positive. Now, if, and I'm put a big if voltage for reaction is negative, then reaction is non-spontaneous. Okay? So I'll put a little poo here. Now, the last thing, if voltage is 0, then reaction is at equilibrium. Okay. Now, some of you might have a little light moment going, oh my gosh, so when my phone dies or my battery dies, does that mean the reaction is at equilibrium? That's right. And this is why when you are able to charge your phone, okay, so when your phone starts to die, okay, what's happening is the overall equation is starting to reach equilibrium. And so when you charge your phone, what's happening is you're basically reversing this reaction, creating more reactants again, and this allows you to generate voltage. Okay? Now, the last thing is this. Notice I put down 1.54 volts. Okay? Now, depending on the combination of chemicals and the concentrations, you would get different voltages. And so this is why in your cell phone batteries, all right, you have your lithium ion. You have other ones that can hold a charge or hold a voltage a little bit better than others. Okay, and it all has to do with what chemicals they have used here in your cell phone. Okay, so you talk about the iPhone, sometimes you get a better battery or a worse battery. That is why. It's what they put into it.